Most programming languages force every condition into one of two boxes, true or false. But real systems don't actually work that way. A sensor that hasn't reported yet isn't false, it's unknown. Two contradictory readings from two trusted sources aren't false either, they're a conflict. Binary truth quietly erases both of those states, and the program has to guess. Semantic starts from a different premise: model the uncertainty instead of hiding it. Semantic's native quad type has exactly 4 values. N means unknown, not enough evidence. F means false. T means true. And S means conflict, incompatible evidence that shouldn't be collapsed into a guess. A quad is not a respelled Boolean. Branching stays explicit. Checking for T is a different question than checking for S, and the language keeps them separate on purpose. Under the hood, quad operations split into 3 families: identity checks that return a plain Boolean, evidence operators that combine quads and return another quad, and selection forms like match that dispatch on all 4 states at once. In the current feature maturity matrix, native quad logic is the one language feature marked as fully executed and stable. Here's a real, working semantic program from the project's own canonical examples. Decision context is a record holding a camera reading, an override state, and a readiness flag, all as ordinary typed fields, one of them a quad. The decide function checks the override first, falls back to the camera reading, and only reaches a T verdict if the system is both cited and ready. Notice the result type: this function doesn't just return a quad, it returns either an OK or an error wrapping one. That forces the caller to handle both paths explicitly. This exact file compiles, verifies, and runs unmodified. Nothing here was written for the camera. Before any of that program runs, it goes through a pipeline. Source text is parsed into a structural model, then semantically checked. Types, records, and control flow are all validated against the language's rules. This is the frontend's job, and only the frontend's job. The compiler does not execute source directly. Parsing, checking, and lowering happen first, and only afterward does the toolchain emit anything resembling executable form. That separation is deliberate. It keeps what the source means apart from how it eventually runs. Once source is checked, it's lowered into a deterministic intermediate representation, then emitted as a versioned artifact called SemCode, a .smc file. This is the artifact that actually gets shipped, verified, and executed. It's not source code anymore, and it's not a live in-memory structure either. It's a self-contained, inspectable binary contract sitting between what you wrote and what will run. Before a SemCode artifact is allowed to execute, it has to pass through a dedicated verifier. This isn't an optimizer, and it isn't a formality, it's a real admission boundary. The verifier checks header validity, function and section integrity, opcode and operand validity, jump targets, call targets, register budgets, and whether the capabilities and artifact claims actually match the operations inside it. A valid producer path does not waive this check. We can watch both outcomes for real. Checking the project's own intentional boundary example, one that tries an import form the language doesn't admit yet, produces a genuine rejection. And taking a perfectly valid compiled artifact and flipping a single byte inside it produces real verifier diagnostics, an invalid register reference, and a call target that no longer resolves to any function. Malformed input doesn't get a best effort pass. It gets rejected, with a reason. Only an admitted artifact reaches the VM. Execution is register-oriented, with explicit call frame management and runtime quota enforcement. The VM will not let a program run forever or blow past its resource budget silently. The trusted route is verifier-first and token-first. SemCode has to produce a verified token before the VM will trust it. Given the same verified SemCode, the same execution config, and the same entry function, the VM is expected to behave deterministically, same result, same trap class, every time. And runtime failures are kept distinct from verifier rejections. A stack overflow, a quota exhaustion, and a verifier rejection are three different, explicitly named outcomes, not one generic crash. The VM has no unrestricted authority over the host machine. Any effect that reaches outside the deterministic runtime, reading or writing external state, emitting an event, crosses through an explicit integration layer called Prometheus, gated by capability checks. If an artifact doesn't hold the right capability, the effect is denied before the host call ever happens. Today, that boundary includes a narrow, capability-controlled print path, enough to observe output from a program, but it's deliberately not a claim of general file access, networking, or unrestricted standard out. The gate exists so external effects stay explicit, not implicit. Let's run the whole pipeline for real, on the command line, against the current build. Check the source. Compile it to a SemCode artifact. Verify that artifact. Run the verified artifact. And disassemble it to see the actual register-level instructions the verifier admitted. Every command here, every line of output, was captured from a real run of the toolchain, not written by hand. So where does that leave Semantic today? The project draws its own lines carefully. There's a published stable line. There's a narrower, qualified limited release contour, covering functions, records, control flow, quad, option and result, sequence iteration, and the full verified execution path, that's been proven against real evidence. Beyond that, current main already contains more, arithmetic, mutable state, loops, text handling, maps, and a capability-gated print path, all landed and benchmark qualified, but not yet promoted into the stable promise. And some things are explicitly out of scope for now: unrestricted standard out, general file or network I/O, a public package registry, a frozen runtime ABI. Semantic is not claiming to be a finished, general-purpose language. It's an emerging verifier-first execution platform, still under active development, that's explicit about exactly which parts of itself are ready. Step back, and the shape of the whole system is the point. Uncertainty is a first-class value, not an edge case bolted on later. Nothing executes without first passing through an explicit admission gate. Execution itself is deterministic and quota-bound. And anything that touches the outside world has to cross a capability boundary that can say no. None of those four properties are common defaults in most languages. Usually you get truth collapse to a Boolean, source that runs as soon as it parses, best effort execution, and host access that's ambient rather than explicit. Semantic makes all four of those choices deliberately, and visibly. That's Semantic, Source flows through semantic analysis into a deterministic IR, gets sealed into a SemCode artifact, has to clear a real verifier before it's trusted, runs inside a deterministic VM, and only reaches the outside world through an explicit capability gate. It's not a finished general-purpose language yet, and it doesn't claim to be, but the architecture is built to keep that promise as it grows. If you want to see it for yourself, the repository is linked below, and every command in this video runs exactly as shown.